Thank you. So obviously we don't have a photo of an actual magma ocean. So I found this really pretty picture of a lava lake near Gango. I'm going to have like a couple of different versions of photos of this lava lake. But you can see this is looking at a pool of lava that is on the surface of a planet, and it's got volatiles coming out of it. So this is sort of the effect we're going to talk about a lot. Is the interaction of lavas and volatile elements in the composition and the evolution of atmospheres on planets with magma oceans. I want to take a minute just to recognize my collaborators, many of whom are here. Kaveh Polivan, our chair, Robin Wordsworth, Edwin Kite, Sukrit Ranjan, and then of course my former advisors, Lindy Elkins-Tanton and Bruce Fagley, and Dimitar Sasolov as well, who I didn't put on this slide. Anyway, so let's start with a little description of what exactly a magma ocean is. And for the purposes of my talk, I'm just going to call a magma ocean anything that is a very large body of silicate melt, which may have some sort of crystals within it that is occupying a large portion of the surface of a terrestrial planet. The figure on the left, on the right here is showing how we usually think that magma oceans are evolving based on the temperature structure within the planet. So this, the red portions here are where we have silicate liquid. Blue portions are where we have solidified magma ocean. And this green down here at the bottom is assuming that we didn't fully melt our mantle, so we have some unmelted residual down at the bottom of the planet. The black curves here are the melting temperatures of the silicate that's making up this planet. And for those of you who don't think about silicate melts, it's important to remember that they are multi-component species, and so they don't have a single melting point. They have two. The solidus is the point at which the first little bit of melt forms in the system, and then we also have the liquidus, which is this curve here, which is where the last little crystal of silicate is finally melting. So in this region in between, we have partial melt. And so we have sort of this dashed line is sort of the dividing line between where we would think of this as more liquid present within a solid matrix of crystals versus a solid sort of floating around in what is dominantly a liquid in this upper region. Okay, so the more or less vertical lines here with the temperatures at the top are adiabats. So we think within the silicate melt portion, within the melt, the viscosity is pretty low, and so these are convecting on pretty rapid time scales. And so the temperature profile of the magma ocean is following an adiabat. And for the purposes of the models that I'm going to talk about here, what we typically assume is that the adiabat first intersects these melting points at the bottom of the mantle. And so what's happening is we get the first little bit of solidification is happening down at the bottom of your mantle, and the remainder, the top, remains liquid. And so if you have an atmosphere, you'll be interacting with the liquid for the duration of the magma ocean time period. There is a little bit of a complication here in that we don't really know the melting profile of super Earths. We don't really know melting profiles much beyond the pressure regime of the Earth's mantle. And even that is somewhat disputed. Some experiments suggest that there is a bit of a curvature to the solidus and the liquidus that would indicate that you should start getting your first sort of crystals forming sort of in mid-mantle regions where you might end up with a basal magma ocean with the planet sort of solidifying in both directions at the same time. But for the models that I'm mostly going to be talking about today, we're going to assume that the solidus is nice and decreasing, and so that we're only going to start solidifying at the bottom of the mantle. So I'm going to split this talk up a little bit into first, where do we find magma oceans, and then talk a little bit more after that about the dominant processes that different kinds of magma oceans would experience. So let's start first with where do we find magma oceans. This is just another schematic of a magma ocean here where we have the convecting liquid and crystals falling out towards the bottom of the mantle. And we have an atmosphere on top. So there's sort of three major places where I think we're finding magma oceans. And these are sort of separated by the dominant heat source that's producing these magma oceans. And I left one off here, which is tidal heating. I'm not going to talk about tidal heating here at all. So the first one I'm going to talk about is young planets, and this is what we usually think of for the solar system. And a lot of the magma ocean models are really based on models developed in the solar system, especially those models developed by Matsui and Abe in the mid-'80s for the formation of Earth and Venus and Mars. So the figure on the left is showing the evolution of the mass and radius of the planet as it is growing from an accretional model. So the radius of the planet is increasing to the right on this x-axis here, and the y-axis is showing the mass of the atmosphere. And so what's happening is volatile material is coming in with the solid material, and it's being delivered into the atmosphere. So you have pretty rapid atmospheric growth. This figure on the right is from a related model from Abe, and is showing the evolution of the pressure and temperature at the surface of the planet as a result of many of these rapid impacts. So we have a rapid increase in the pressure as the mass of the atmosphere is growing, and because these collisions are occurring quickly and heat is not being dissipated, the surface temperature of the planet is growing. And it's growing here in a stochastic way because these are impacts of variable size and variable duration, and so forth. So this is sort of the standard picture that came out in the 80s and early 90s for how planets grew in the solar system and how the early atmosphere grew. And this implies that you have these massive surface temperatures that would require the planets to become fully molten all the way through. The other method, in addition to just this sort of singular, many small impacts could produce this magma ocean. Now the more favorable method for doing this is a singular giant impact, such as the one that we think created the Earth's moon. In fact, the moon is actually the only object in the solar system for which we have solid evidence that there, in fact, was a magma ocean. Every other planet, including the Earth and Venus and many of the small planetesimals that people think had magma oceans, it's all very circumstantial. But for the moon, people had originally thought that when the first Apollo samples came back, the composition of the crust of the moon is shown in this sort of diagram over here. This is sort of a less colorful version of that diagram from 1970. The crust of the moon is made of this component called anorthosite. It's dominantly made out of the mineral anorthite, which is a very light, low density mineral. And the way people thought that this was created, this crust of anorthosite, is that you have a magma ocean created as the moon is forming by this giant impact. You melt most of the planet, and then you begin fractionally crystallizing it. And so what that means is that you're crystallizing different minerals out of the silicate melt within the magma ocean, and it's separating out. So those minerals are falling down to the bottom of the magma ocean and separating from the melt. And so the melt composition is evolving, and so the minerals that are coming out next have a slightly different composition. Once you get to a certain fraction of melt crystallized, you can begin to crystallize this mineral anorthite, which turns out to be lower density than the silicate liquid it's crystallizing out of. And so what happens is it floats. It floats to the top, and it makes this rich crust of the early moon. And this process had been seen before on the Earth in magma chambers. We had seen anorthite flotation crust within magma chambers. And there are other pieces of evidence for the lunar magma ocean, including there's a component called CREEP, K-R-E-E-P, for potassium, rare earth elements, and phosphorus. This appears to be sort of the residual of the magma ocean. It's the last little bit that crystallized, and it has all the incompatible elements that didn't want to freeze out in the earlier stages of crystallization. And then the other sort of evidence for lunar magma ocean comes from the ages of these crustal materials that were brought back by Apollo and from lunar meteorites. This is a timeline of lunar formation and differentiation from Lindy Elkins-Tanton's work on the lunar magma ocean, where you can see lunar formation from giant impact is out here, about 4.54 billion years. And you have the magma ocean, the formation of the moon from the disk of material that's ejected from the Earth. These bars over here are ages for lunar crustal materials, and these are quite a bit older than most of the other materials that we have access to from planetary sized bodies, and much older, in fact, than anything that we have from the Earth. And then these blue bars are highlighting the predicted magma ocean lifetimes from models. Initial models put the lifetime at only 10 million years, which wasn't really enough to account for the ages of these many different minerals from the lunar surface. But the addition of tidal heating allowed the extension of this crystallization timescale. So this is, this is amongst the best evidence that we have that magma oceans are a real phenomenon within the solar system. Now, the giant impact would have almost inevitably also melted the Earth, but again, we don't have much in the way of geologic evidence from this time period on the Earth because the Earth is a very geologically active body. But we think it ended up with a massive atmosphere, and it cooled, relatively quickly compared to many other planets. And we think that these giant impacts are pretty common in planet formation. This is from the work of Eliza Quintana, looking at giant impact frequency in in-body simulations of planet formation. And what she found was that for any given object, if you track its impact history, many of them experience on the order of 2 to 3 giant impacts before the accretionary period is over. So the Earth, likely the giant impact that formed the moon, wasn't necessarily the first giant impact generated magma ocean that the Earth experienced. Okay, so moving on from young planets, so that's how you would potentially generate magma oceans on large planets as they are forming. Amongst the exoplanet population, we now have evidence for planets that are extremely hot, and they are likely bare, rocky planets, but nonetheless may have a magma ocean on their day side at least. This is just a mass radius diagram where the planets are color-coded by the flux that they receive and converted here into an equilibrium temperature. So I don't need, and this is a sort of an artist's impression of CoRoT 7b, which was one of the first super Earths discovered by the CoRoT mission, shortly followed by Kepler 10b, which has a very similar orbital period and equilibrium temperature. So these first planets that we discovered in the super Earth regime, they have super Earth, Earth-like densities, but they have temperatures, equilibrium temperatures of around 2000 Kelvin. And most basaltic melts form at temperatures of 1000 to 1200 Kelvin, some up to 1500 Kelvin. So this is more than hot enough just from the stellar insolation to melt the surface, the day sides of these planets. And then the last kind of magma ocean planet that I want to talk about is these sort of hot runaway greenhouse planets that the heat source here is still stellar insolation, but the stellar insolation isn't sufficient without an atmosphere to melt the surface. And in some ways, these are also related to the young planets because we think magma oceans on the young planets are related to this greenhouse effect. But the main component of atmospheres that people with solar system modeling history like to use is water, because water is one of the most abundant volatiles. We don't see hydrogen, helium atmospheres on rocky planets in the solar system, And so this is the dominant volatile component. And it's a very good greenhouse gas. And so this is just a simple calculation that I did with sort of a gray atmosphere model to see how much water you would need in the atmosphere of some of the known super Earth planets in order to bring the surface temperature up to 2000 Kelvin. So the x-axis here is stellar insolation relative to the Earth, with the Earth on the far left-hand side, and this y-axis is the pressure of water vapor in the atmosphere needed to melt the surface. And for reference, this dashed line here is the amount of water on the surface of the Earth today. That's about 300 bars. And so most of these need around 1 bar, 10 bars. Now, whether that's a stable atmosphere or not is a different matter, but they don't need very much atmosphere at all to cause their surfaces to melt. This is a very well-known subject that people have studied a lot, this runaway greenhouse phenomenon for water-rich worlds. This is a calculation of the runaway greenhouse limit for a steam atmosphere from Keiko Humano in this review paper by Ikoma. This is the outgoing long-wave radiation from the planet as a function of the water vapor pressure in the atmosphere. So you can see that as soon as you get above this runaway greenhouse threshold, as you add water to your atmosphere, you have to get out to really, really hot temperatures in order to hit radiative equilibrium. So if you say have 100 bars of water vapor in your atmosphere and you're receiving 1,000 watts of stellar radiation, then your surface temperature is around 2000 Kelvin. Okay. So I wanted to highlight here a poster by Nishika Jha on this kind of steam and CO2 mixed atmosphere. So you should go check out her poster. Keiko Humano has looked at sort of the magma ocean occurrence as a function of stellar age and orbital distance for G-dwarf stars. The color coding here is the amount of water a planet needs to have to maintain a magma ocean for this stellar age. These are planets orbiting G-dwarfs. She's highlighting here the giant impact stage. So planets out here at Earth orbit cannot really maintain a magma ocean beyond the giant impact stage. The magma oceans cool off much too quickly. There's this sort of critical orbital distance at which point, at some point, the planet cools off to the point where you can get liquid water to form. And once that does, the runaway greenhouse atmosphere collapses and you get a significant drop in your surface temperature. So for this sort of Venus-like orbital period, you get this sort of peak if you have like one Earth ocean of water in the length of time that you can have your magma ocean surviving. And of course, the more water you have, the longer your magma ocean can survive. Okay, so I'm going to jump now to talking about some of more of the dynamics and the chemistry of the processes going on these different kinds of planets. I'm going to come back to those planets that are very volatile rich, and I'm going to start first of all with the lava worlds discovered in the exoplanet sample. And I'm going to start with with some of the initial models that were based on CoRo 7b and Kepler 10b. This is sort of an artist's impression from this big paper by Alain Laguerre and many, many co-authors. So this is an artist's rendition of what this planet would look like. The assumption being that this planet is tidally locked and synchronously rotating. And so it has a permanent day side and a permanent night side. And that permanent day side is covered with a lava pool with, of course, the peak temperature occurring at the substellar point and dropping off rapidly towards the terminator. And so the edges of this magma ocean pool are going to occur before you hit the terminator because the terminator is quite cold. And the atmospheric pressure is determined here under the assumption that these planets are volatile free by a silicate vaporization model. So this was based on some of our previous models that we had actually developed for modeling the composition of volcanic gases on Jupiter's moon Io. This is the predicted gas composition as a function of temperature for a silicate melt, where the dominant gas here is sodium, because sodium is a very volatile, relatively volatile element in a silicate system. And the next most abundant gases are oxygen and O2, because oxygen is, in fact, the most abundant element in silicate melt systems. And then you have things like silicon monoxide and magnesium and iron atomic species. And this model also looked at fractional evaporation of this system. So if you have a massive pressure gradient, you should expect to get winds driving away from this substellar point where most of your material is evaporating, and might cause some compositional evolution of this pool. And this model handles the fractional vaporization. The x-axis here is the fraction of the silicate that has evaporated. And this is showing the composition of the gas phase. So what you see is that the sodium and potassium are depleted the first from this melt pool because they're the most volatile elements present, followed by iron. Iron is in fact very volatile. And afterwards, you have a composition mostly dominated by silicon magnesium. And if you keep going far enough, you'll get out to a composition dominated by calcium and aluminum. Ito et al. In 2015 did another round of calculations of this kind of silicate vapor atmosphere, and they calculated temperature and pressure profiles for different sort of substellar equilibrium temperatures. And what they found was that once you get above an equilibrium temperature of about 2000 Kelvin, you end up getting a temperature inversion in the atmosphere. And then they calculated the secondary eclipse depths for a variety of these lava world planets from the infrared out to the optical out to the far infrared. And you get some features coming from the atmosphere. You have sodium and potassium lines in the optical, and these features here, I believe, are due to the silicon monoxide gas. And so those are potentially observable with James Webb. And the other observational test you can make for these planets is to test whether, in fact, you have heat redistribution from the day side to the night side, in which case you would expect a lower temperature contrast from day to night, and that would potentially indicate that rather than having lost all their volatiles, they might in fact still have a significant volatile envelope. So Edwin Kite led a study taking this model for the silicate evaporation of this melt pool and included some more dynamics to it. So what he found was that you get evaporation at the substellar point, but in fact, you get condensation of that material back onto the pool before you reach the terminator or the edges of the pool. And you'll get additional evaporation from out here. And so, in fact, the regions where you're losing more of your mass is coming from the edges of the pool because it can leave the boundaries of the pool before recondensing. And so you do still have this flow of material coming from the day side, from the substellar point, moving around to the night side. But mantle convection should be sort of replenishing this pool from the bottom of the pool. The convection within the pool is sort of determined by the composition and the density evolution of the chemical boundary layer at the surface. So the solid line in this figure is taking the evolution of that surface layer and calculating the density of it. So this is the sort of the residual material density. And so you can see that this is for a bulk silicate earth sort of composition, which is relatively low in iron oxide. And you get a marginal decrease in the density of this surface layer until you get out to here where it's initially returns back to the same. And the highest density you get is out here at about 70% evaporated. But what happens if you have more iron oxide in your bulk composition? is that the evaporation of that surface layer produces material that is lower density, and so it's buoyant. And so this upper layer remains buoyant, and you never get full overturn of that layer. And so this layer can evolve into becoming more calcium and aluminum dominated, and you would expect these kinds of planets to have sort of compositionally uniform but evolved surfaces of this sort of composition. For materials that have less iron in their bulk composition, this fractional vaporization leads to this boundary layer becoming denser over time, and so it will eventually overturn. And so you can get variable and patchy surfaces, or sort of uniform surfaces depending on the relative timescales of the chemical and the thermal overturn times of these planets. So I think these planets are extremely interesting, and I think there's a lot of interesting work still to be done on them in order to understand them better, and hopefully observations with James Webb would be able to improve our understanding here. But I think some outstanding questions on these planets are these lava planets in fact completely devoid of volatiles? This was sort of a starting assumption that we made, and it hasn't really been tested. If they have a thin volatile envelope, that might not be distinguishable from the mass and radius of the planets, but potentially could be determined from secondary eclipses. The reason, obviously, that this problem hasn't been done is because, as James Owen was telling us earlier, these escape problems are pretty hard, especially when you're talking about heavier elements and not just hydrogen and helium. So then the question is, how much of if these are just silicate planets, how much of the heavy elements can evaporate from them? Can you start to lose sodium from your planet altogether, for instance? And then the model here of this lava lake sort of assumes a synchronous rotation. And the question is whether this is valid for all of these planets. Have they all fully, most of them are likely fully tidally locked, but what about true polar wander? Jeremy LeConte has showed that this is possible for planets in the Hadal zone. Is this possible for these close-in planets? Possibly not all of them, but maybe a subset of them would not be fully synchronously rotating. And then what are the implications for the surface environment of this planet? So now I'm going to switch gears again from this and leave you with those open questions for lava planets and go back to more volatile-rich planets and talk about volatile and magma ocean interactions. And I like this figure of this lava lake again, because you have these gases coming out of it. That's really emphasizing that the volatiles are actually coming out of this lava. They're dissolved in the lava here. And so there's a real interaction between lavas and the atmosphere in these kinds of systems. So the water will partition as the magma ocean crystallizes and cools off between the melt and the solid. Within the Earth's mantle, there's probably at least the same amount of water as there is on the surface, possibly more, although that is still pretty highly debated. This figure on the left is showing the solubility of water in different minerals within the Earth's mantle today. You can see there's a region here called the transition zone where there's potential for a lot of water storage capability, but it's not really known yet whether there is actually water, this much water in that region. So the water, once the magma ocean starts to crystallize, will be stored in these nominally anhydrous minerals like olivine. So olivine is Mg2SiO4. It does not have water in its chemical formula, so the water is stored in small spaces in the crystal lattice, mostly as OH groups. But the abundance of water that you can store in the olivine is dependent on the pressure and the depth within the planet. And within magma ocean models, we parameterize the way that water will partition between the melt and the solid phase by a partition coefficient. So these are based on experimental measurements of how water will distribute itself in a system. So this is just the concentration of water in the crystal phase divided by the concentration in a coexisting melt phase. And for many of the minerals found commonly within the Earth, that value is below 1, which indicates that the water actually wants to stay as long as it can in the melt phase. And so what happens is that as the magma ocean starts to crystallize, water will become more abundant in the melt phase. But you will still always retain some amount of water in your solid silicate minerals. This is showing the solubility of water and CO2 within different kinds of silicate melts. So this is as a function of pressure for both of these. This is water and CO2. The solubility is somewhat dependent on the actual composition of the silicate material. And so, we take models for the Earth and apply them to exoplanets, but understanding the composition space of the solubility for many of these volatiles is going to be very important in the future. So water has a high solubility. CO2 is somewhat soluble, but it will actually partition more preferentially into the atmosphere than stay in the melt. The other thing is that these volatiles actually interact with each other within the melt phase. And so if you have both water and CO2 dissolved within the melt, they limit each other's solubility. So along an isobar here, this is 1 kilobar. If you have 400 parts per million of CO2, you're limited to 2 weight% of water, for instance. So this is because the volatiles are reacting to the mutual pressure of the fluid. The volatile solubility within the melt also depends on a factor called the oxidation state or the oxygen fugacity of the system. This is a compilation of different volatiles dissolved within silicate melt as a function of oxygen fugacity. And I have a quick slide here just to explain very quickly what oxygen fugacity is. Within a gas phase, you can consider oxygen fugacity just the partial pressure of the oxygen. But within a solid or a liquid phase, the oxygen fugacity is more of a potential measure of the relative abundances of elements that have different valence states. So that is within a silicate, the dominant element that is controlling this is iron. So iron has 3 major valence states within a silicate planet. That is metal, which is found in the core predominantly. There's iron 2+ and iron 3+. And so this valence state is determining how much oxygen the iron can react with. So if one of the dominant controlling reactions, especially during core formation, is this iron-wüstite buffer. So the presence of metal will limit the amount of the oxygen fugacity of the system. But the oxygen is reacting with the metal and making this iron 2+. And the oxygen fugacity is within an outgassing system will also control the composition of the gas phase. So the oxygen fugacity is proportional to the relative abundances of, say, water vapor to hydrogen or CO2 to carbon monoxide. So to go back to this figure of the volatile solubilities, at low oxygen fugacities, we favor reduced forms of the volatiles, like methane is the dominant form of carbon. As you go to higher oxygen fugacities, you favor more oxygen-rich volatiles like carbonates, for instance. Molecular hydrogen, which is shown in this figure here, is much more soluble in melts that have a low oxygen fugacity, and at higher oxygen fugacities, you favor water as the hydrogen-bearing species. So I encourage you also to go look at the poster of Sakuraba, who is looking at volatile partitioning during impacts on the early Earth. Okay, and water also influences the melting point of silicates. This is, I showed you earlier, a model of the solidus and liquidus of the magma ocean. Many times we assume a dry solidus. This is where we're looking at the measured melting point of a system that didn't contain water. But we know, in fact, that if you add water into that system, you lower the melting point, sometimes substantially. So these are 3 very different parameterizations for the wet solidus for the Earth's mantle. So you can see that some of these would predict that the Earth's mantle should melt at 200 or 300 Kelvin lower than you would predict if the mantle were dry. This can also influence magma ocean solidification times. This is just a comparison of solidification times if we assume a dry solidus in this blue curve versus with the wet solidus in this red curve. So if you have a large amount of water in your system, you can potentially increase the amount of time it takes your magma ocean to solidify pretty significantly. One thing that people have brought up a couple of times now is this idea of a fuzzy core for giant planets, potentially for sub-Neptunes, and I think also for these steam atmosphere planets. At some point, water and rock become fully miscible within one another. So water, we know, is in small quantities soluble in the rock or in the melt. At high pressures and temperatures, the water rock mixture is a single fluid. So this is the phase diagram for the basalt water system. Basalt's a very common melt on the Earth. This is showing at pressures below this critical point, you have for most of this phase space, you have a basaltic solid and you have a basalt, a fluid. Then you get above the melting point of the solid, and now you have solid and melt, and then you have a melt. And you have over here a separate water-based fluid. Once you get to higher pressures above this critical point, now you only have one fluid. Okay, and the conditions here are not very extreme. This is about 5 gigapascals and about 1300 degrees C. So at some point within these exoplanet systems, we may reach the point where we have fully miscible water and rock system at high pressures within the interior of our planet. This was a concept we first discussed at a workshop back in last February, February 2018, that Tim Lichtenberg had organized at University of Zurich. Yeah, so the question is at what sort of envelope mass and planet mass do we stop having this sharp boundary between the silicate mantle and the envelope? I think that's a very interesting question for future research. One other thing I wanted to point out about the silicate melt and the effect that water has on it is the density of the melt. This is a figure on the top left here, top right here, showing the density of a prototype melt. Prototype's sort of the analog for the Earth's mantle, as a function of the water content. So you can see it's going from about 3.7 grams per centimeter cubed down to about 3.2 if you add 20 weight% of water into this melt. This is at about 15 GPa. Over here on the left, I've calculated the equation of states, the densities as a function of pressure, and comparing it just with the standard solid silicate model that most people use for mass radius diagrams, which is this blue curve. The red curve is the dry silicate melt, and then this yellow curve is the hydrated silicate melt with about 5 weight% water. And you can see this is affecting mostly the upper layers of the planet, but that's where you're going to get the largest radius increase. So potentially we are sort of underestimating radius for planets that have a magma ocean. And I also recommend you go talk to Edwin Kite about how hydrogen and silicate melts might affect the radii of sub-Neptunes. In terms of other processes going on in the magma ocean, the degassing process is one that really requires a lot more study because it's not clear whether we have what model of degassing can actually be achieved within a magma ocean. Most models, including my own, assume continuous degassing. So that's sort of highlighted by this upper row of figures here. And what we assume is that the silicate melt at some point reaches its saturation point at the surface, and then it outgasses some amount of volatiles into the atmosphere to remain at that saturation point. And this is controlled sort of by the diffusivity of the volatile out of the silicate liquid. Observations of silicate melts in lavas on the Earth and looking at lava degassing suggests that some amount of degassing is controlled by bubble formation and bubble nucleation. So this is work from Jenny Sucali, and she suggests that there might be, in some situations, instead of this continuous degassing, catastrophic degassing. And so catastrophic degassing would, in order to nucleate your bubbles, you actually require an oversaturation of the volatile within your silicate melt. And you also require the presence of nucleation agents. So you have to have some kind of crystals and sort of the right kind of crystals floating around in your silicate in order to allow bubbles to nucleate and then allow them to percolate up to the surface where they can degas. So the idea here is that there might be some hindrances to this happening, this bubble nucleation process. You don't get to this supersaturation point, for instance, and then the degassing would occur very catastrophically, sort of at the very end stage of the magma ocean, when you do enrich your melt much more in the volatiles. And this would be by compaction of the cumulate. So you have crystals floating in your liquid, and the bubbles are sort of trapped within that mush of crystals and liquid. And so it's once those start to compact under their own self-gravity that the bubbles would be free to escape. And so this might happen in sort of localized occurrences and sort of catastrophically at the end stage of magma ocean. And then there's a possibility that some planets may have minimal to no degassing, and this is if they never have enough volatiles to reach this saturation condition for either the continuous or the catastrophic degassing. So at some point, you might have a planet with a low enough volatile abundance that most of the volatiles are going to remain trapped within the interior of the planet. I'm going to skip the next slide for time and switch on to looking at some of the actual models for these planets. This is going back to work by Keiko Homano, and she was again looking at the two types of planets that you might have depending on the orbital period of the planet. So these are sort of Earth and Venus analogs, where you have type 1 planets are far enough away from their star that the water, this is again with the assumption of a water vapor atmosphere, that they can cool off without losing much atmosphere and eventually form an ocean. So the cooling timescale here is a few million years for this Earth-like planet, and you get water collapsing out of the atmosphere into an ocean. In contrast, for type 2 planets like potentially like Venus, what happens is that they remain in the magma ocean phase for a much more extended period of time, and they have this water layer in their atmosphere, and some of it starts to escape. And so in Keiko's models, actually the magma ocean only eventually cools off because you lose enough water for the surface to finally start to cool off. But there is never any condensation of water in these models. So James Owen brought this paper up in his talk, but I'll come back to Luer and Parnes, who showed this for exoplanets for M-dwarf habitable zone planets. They were looking at how the stellar radiation changes with time and stellar mass. So this is a calculation from their paper of the fraction of runaway greenhouse flux that a planet on the inner edge of the habitable zone receives over the course of its lifetime for stars that are sun-like down to 1/10 of a solar mass. And so again, this kind of planet would remain in the magma ocean phase if it has a runaway greenhouse atmosphere for most of its lifetime. And this then leads to the problem of escape of the atmosphere. And James showed this as well. This is water lost from these planets through this energy-limited approximation for the atmospheric escape, where the assumption is that the water is photolyzing in the upper atmosphere and you're losing most of the hydrogen and some amount of the oxygen. So here, red is complete loss of one ocean mass of water. And then the oxygen builds up in the atmosphere, especially for these intermediate mass stars. You get up to 300 bars of oxygen in the atmosphere. So what we wanted to look at was to try a similar kind of model and see how actually the oxygen would react with the magma ocean itself. So we originally did this, myself, Robin Wordsworth, and some other collaborators at Harvard, did this for GJ 1132b. Many of you are probably familiar with this planet. It's around an M-dwarf star, about 0.2 solar masses. It's very Earth-like in density. It's not in the habitable zone. It's about 400 Kelvin equilibrium temperature. But we wanted to look at this planet and see if it were possible for it to continue outgassing over the course of its lifetime, and whether it would have some kind of residual atmosphere that we could observe. So this is the magma ocean model. Just again, we have water dissolved in the magma ocean, in the melt. We're solidifying from the bottom up, and we have this atmosphere that's, the pressure of this atmosphere is set by this continuous degassing limit where we're at saturation at the surface. And we have XUV radiation hitting the atmosphere. And we're assuming the sort of energy limited escape formula. And so we compared results for two different models for the XUV flux evolution of the M-dwarf, and for James, we used an efficiency factor of 0.3, so maybe a little high. And then we looked at the results for a range of initial water abundances for the planet and iron oxide abundances for the mantle. And this is where the oxygen is reacting out of the atmosphere and into the planetary mantle. And I'll also highlight Robin Wordsworth is going to talk about a further development of this model for habitable zone planets tomorrow. So this is just a quick example of a magma ocean evolution calculation where we're modeling the thermal structure of the planet, how it cools over its lifetime. The magma ocean is effectively over when this is the surface temperature and the mantle temperature diverge. And here we get a solid surface. And so we no longer have atmosphere and mantle exchange going on. This bottom figure is showing the evolution of the water inventory between the magma ocean, which is here, the atmosphere in the dashed line, and the dotted line is within the solid mantle. So you can see we always have some amount of water remaining within the mantle's interior. So the magma ocean lifetime depends very strongly then on the initial water abundance for the planet. This is going from a few million years out to a few billion years, depending on also the XUV flux. So again, this planet often can only cool off if it loses all of its water. This is highlighting sort of the range of lifetimes that we expect for the Earth's magma ocean and the Earth's water abundance. And this is the amount of water that the planet is left with at the end of these simulations. So these are 5 billion years long. Again, this is the initial bulk water abundance. And this is the fraction of water that is lost from the planet depending on these XUV models. So the pink indicates that for this low XUV model, we actually have a fair amount of water left within the planet, but it's all trapped within the mantle, as I'll show you here. Okay, so that's again the Earth's water. So then to go to the oxygen is taken up in the magma ocean, again, by reaction with iron because it's the dominant element that has this multiple valence states within the silicate melt. Often we think in magma ocean models that we're starting only with the iron 2+ form. And so here we set the initial iron 3+ to 0 and allow reaction as the oxygen diffuses back down through the atmosphere with the melt to make this iron 3+ form. And here are the results for the atmospheric oxygen abundance at the end of this 5 billion year evolution timeline. So this is showing the high XUV and low XUV models. This is for iron oxide in the planet's mantle and the initial water abundance. So for this high XUV model, we essentially end up with really no atmosphere left on this planet. We would, if we go out and observe it, we might expect to find a bare rock. If the atmospheric evolution has slightly lower XUV, then we might expect sort of a tenuous oxygen atmosphere. And there is still water on this planet, but it's trapped in the interior. So there might be some slow, leaky outgassing coming from the planet's interior. At higher water abundances, we get sort of moderate oxygen levels of a few bars. Again, no real water left. But if you go up to these sort of extreme initial water abundances of 10 to 20 weight percent, which might be above the limit where the model starts breaking down, you retain this thick water atmosphere. You have several kilobars of oxygen in the atmosphere, and these planets are still in this magma ocean stage because they haven't cooled off. And they can't cool off because they have too much water. If we look at what happens to the oxygen for these planets, actually most of the oxygen escapes. So this is showing the fraction of oxygen that remains, that actually reacts with the mantle of the planets. Again, this is the water and iron in the mantle. The color here is the fraction in percent of the total oxygen remaining. So this is about 8 to 10% of the oxygen remains within the mantle. And this is for the low XUV model. For the high XUV model, in fact, almost all of the oxygen escapes. But as James Owen mentioned, the oxygen might in fact be a coolant in this outflow. And so it's not clear exactly how well this energy limited formula for the oxygen escape is working. So if we limit the oxygen loss, so we turn it off and run the model again, then what we get is that, in fact, most of the oxygen reacts with the planet's mantle. This is up to 90% is reacting. And this dividing line here is essentially because, well, we have too much oxygen being produced from this water and the mantle can't hold on to it. It doesn't have enough iron oxide down at this upper left-hand side. So we have more mantle oxidation when there's no oxygen loss, up to 90%. Okay, and then that leads me very quickly to talk a little bit about the evolution of the Earth's mantle oxidation state. We can measure the Earth's oxidation state both at the present day through looking at basalts and other material coming out of the mantle. And we get values around this quartz phalite magnetite buffer, which is quite a bit above the iron wüstite buffer that I talked about a little bit before. And we have measurements of proxies going back to about 3.8 billion years, which is sort of the limit of our rock record. And it seems to have a pretty constant value. And so people have long assumed that the composition of volcanic gases coming out of the Earth's interior has been essentially the same over geologic history because of this constant oxidation state. During planet formation, however, when there's metal present and reacting with the magma ocean and reacting with the silicate mantle, the predicted oxidation state of the Earth is down here. It's 8 log units below the present day, or down to 8 log units. And so there have been a lot of models to try to explain this over time through various mechanisms, by accretion of oxidized material, by slow oxidation of hydrogen loss. Maybe you have very slow change in oxidation state over this first half a billion years. But I'm going to talk you through very quickly a possible oxidation mechanism that's related solely to the chemistry of the silicate melt. And then I'm not going to talk about this actually because I won't have time. So this is a process that happens during core formation, and it should be pretty intrinsic to the process for many terrestrial planets. And what happens is, so we have both silicate and metal being delivered to the planet as it's growing, and we have some equilibration going on between the silicate and the metal. In fact, we think that there is some amount of silicon and oxygen present within the Earth's core today, and that's because the density of Earth's core is slightly below that of pure iron, and which is why I'm including these reactions here. So we have iron metal reacting with silicates in the liquid, and you get some amount of silicon and some amount of oxygen going into your metal phase that is then sinking to the bottom of your planet and forming your metallic core. And that's governed by these equilibrium constants over here. Here's a very complicated formula for this that has been calibrated from experiments. And then the other reaction we can add into this now, because we now have some new experimental data on silicate melts at higher pressures, is this reaction down here at the bottom. So what this reaction is showing is that we have the mantle is dominated by this iron 2+ in the silicate melt. But at high pressure, what happens is the volume change of this reaction shifts in favor of iron 3+. So at high pressures, iron 3+ becomes stabilized. And in order to charge balance this reaction, you have to also produce some metal. So this is kind of complicated, but what happens is if you can separate this metal at the time that this reaction is happening, remove it from your mantle system, now you've effectively increased your iron to oxygen ratio in the mantle. And this is connected, of course, to outgassing through the oxygen fugacity of the system. So the higher the iron 3+ abundance, the higher your oxygen fugacity is going to be. So we've done some calculations using some newer experimental data on this. Prior calculations would put the iron 3+ abundance within the silicate melt as a function of pressure along this green curve here. And so core formation, we think, happens at pretty high pressures, up to 50 to 60 gigapascals within the planet. And that pressure should probably grow as a function of planet size. But so this original low pressure data would suggest that you don't really produce any of this iron 3+ in the mantle. But this new experimental data gives us this curve up here, which at the conditions that we think for the average core formation conditions of the Earth gives us about 1.5% of iron 3+, and that matches the present day. So with this new data, we can now match the oxidation state of the Earth's mantle during core formation. So I'm going to skip through a lot of this because it's complicated, but what happens is that you have, during this time of core formation, you have a really low oxygen fugacity, and so you expect really reduced gases like hydrogen, H2, and carbon monoxide to be your outgassing species. As you increase the oxidation state of the mantle, you should expect a shift from that kind of composition to more water and CO2-rich atmospheres. And so because this reaction is a function of pressure of this reaction, it might be a function of planet size as well. And so you might expect a shift in the oxidation state from smaller planets being more reduced to larger planets being more oxidized. Done? Okay, so I'll just skip really quickly from that. So by the time our planet is fully formed, we should be at an oxidation state, for the Earth at least, where we favor water and CO2 compositions. But this is a calculation that we did for the bulk silicate Earth, where you can see that it's not just water and CO2 in this atmosphere. There's a lot more minor species like sulfur dioxide. You have a lot of lithophile elements, and these are all contributing to the spectra. They're contributing to the rate at which the planet is cooling from the upper atmosphere. This is a calculation of the emission spectra of the top of the atmosphere that Roxana Lupu did with these gas compositions compared to models of pure water. This is a model of 90% water and 10% CO2. So that composition on the previous page is in the red. The blue is another complicated continental crust composition. And you can see a significant difference in the spectra of this planet. This could be observable in, for instance, giant impacts. This could be observable in these hot exoplanets that have surface magma oceans caused by the steam atmosphere. But it also affects the cooling timescale for Earth in particular. So I'll just bump through this really quickly. This is the cooling timescale. If you take that continental crust-derived atmosphere, you get a cooling timescale for the Earth's magma ocean of about 200,000 years. For that bulk silicate Earth composition, you get 2 million years. So that's a factor of 10 in cooling timescale. Okay, so with that, I am going to jump to my conclusion slide, and I'll tell you, I think one of the big things to take away from this is that the planetary oxidation state is determined during the magma ocean stage for many planets. It might be a function of the planet's size, but I think we really need some improved models to understand the evolution of oxidation state for both Earth and other planets. And then I think there's a lot of interesting, outstanding issues to work on for the lava worlds, whether they have volatiles or not, whether they're synchronously rotating, the runaway greenhouse planets, what their atmospheric compositions are, what their spectra are, and whether atmospheric escape is sculpting their compositions. And then we need a lot of experimental data. So if you were inspired by Maggie's talk earlier and want to get into experiments, there's plenty of things to measure. Okay, so with that, thank you.
Okay, we covered a lot of ground, but we have question for time for maybe 1 or 2 questions. Yes. Oh, no, okay.
Thanks, Laura. Great talk. This might be a very naive question, but at the very lower planet size regime, is there any evidence that Mercury had lava oceans and or outgassing, and could any constraints on that be used to help inform the interior cooling rate models for that very low size regime?
Right. So there has been obviously suggestions that Mercury lost a lot of its mantle due to a giant impact, and then you would assume that some portion of the remaining planet might have melted as well. We don't have really good evidence from the present set of observations for a magma ocean, but you know Steve Dash, he has a model.
Does anyone have a burning question? Oh, yes.
Great talk, Tad Kamasic, U Chicago. So a couple people in this room a couple of years ago tried to explain 55 Canker-E's thermal phase curve using hydrogen-nitrogen atmosphere. Is that is that okay if there's a magma ocean, a lava ocean, or is that not okay chemically?
I mean, I think you could definitely still have a magma ocean with a hydrogen-nitrogen atmosphere. I think the question for me is whether a hydrogen atmosphere is stable against the escape. Certainly, I think that planet has to have some kind of atmosphere to explain its lower density. Yeah.
Yeah, I'll just comment that, as Mark and I said in the paper, we don't think that a hydrogen atmosphere is actually plausible because of the escape problem. But if you really believe the phase shift of the hotspot, that forces you in the direction of a hydrogen-rich atmosphere, which is really problematic.
Right. And in order to account for the HCN observation, if you believe that observation, it's hard to do that without some significant hydrogen-bearing species like methane or hydrogen.
Okay, let's thank Laura again.